Right, it's time for question 2. Question 2, AC circuit theory. The LCR circuit shown in the diagram is in resonance. It's a big hint. The inductor and capacitor are both ideal. So what we have is an inductor, a capacitor, resistor. We've got an ammeter telling us the current. We've got a source. We're told the frequency, that's labelled there, 5 times 10 to the 2 hertz. We're told the inductance, L equals 1.013 times 10 to the minus 2 hertz. Actually, I should write this thing about significant figures, 5.00. They're giving us those significant figures. I note that L has 4 of them on there. C is 1.00 times 10 to the minus 5 farads, and R is 10 ohms. And the question is, show that the voltages at resonance across the inductor and the capacitor are both 79.6 volts, and explain why voltages larger than the source voltage are created. The source voltage is 25.0 volts, and we're told 79.6 there, 79.6 there. Okay, so AC circuits. We've got obviously a current flowing around the circuit. It's a series circuit, so the current is the same in all the elements, so we know that for sure. If we know the current, we do, 2.50 amps, we're given that, and we know the inductance, we know the capacitance, we can find the reactance of each, and therefore we should be able to relate the current to the voltage. Well, let's start with the inductor. So we know the reactance of the inductor is omega times L. The inductance, where omega is your angular velocity, 2 pi f. And that, of course, is going to equal the magnitude of the voltage over the magnitude of the current. And running a light, as magnitudes are 2, because it's an AC circuit, voltage and current are not in phase. So, what is the magnitude of the voltage? So, magnitude of the voltage is just omega 2 pi times the frequency times my inductance times L times the size of my current. So that's 2 pi times 500 hertz times L, which is 1.013 times 10 to the minus 2 henries, times my current, 2.50 amps. What does that come out as? Time for the calculator. So it's 2 times pi times my frequency 500 times my inductance 1.013 times 10 to the minus 2 times my 2.50, and I'm getting 79.6 volts, which is reassuring. With this sort of thing, doing a calculation, good idea to do a sanity check. 2 pi is about 6, times 5 gives you 30. The 100 there cancels with that there, so we've got 30 times 1, which is about 30 times 2.5. That gets you to 75. So, looks about right. So, happy with that one. Capacitor. Let's go over this way. So again, XC, in this case, is 1 over omega C for a capacitor. Again, magnitude voltage over magnitude of current. So your voltage equals your current over omega times C, which is your 2.50 amps over 2 pi times your 500 hertz times your C, 1.00 times 10 to the minus 5 farads. Stick that in. We hope we get the same thing. Don't be tempted to cheat by just saying it's 79.6. Indeed, 79.6 volts. 3 significant figures. We've got 3 significant figures over here. So we're happy there. That's the first part of part A. Remember there's 2 parts. Show that they're both 79.6 and explain why voltages larger than the source voltage are created. Now, we may have a look at some phases here. AC circuit, CLR. The thing to remember are the phases. For the resistor, the voltage and current are in phase, but they're not for the capacitor and the inductor. Now, it's a series circuit, so current is shared by every one of these. So if we have our current phase pointing along there, that way, in our inductor, the voltage leads the current by 90 degrees. So if our R, voltage over R goes that way in the same direction, in our inductor, the voltage leads the current. In our capacitor, the voltage trails the current. Now, a resonance, these two are the same. So what is the total voltage around the loop? So Kirchhoff's second law says that the voltage there plus the voltage there plus the voltage there equals that, but it's not 79.6 plus 79.6 plus whatever that is, IR25, because these have different phases. So if we add these vectors at resonance, this precisely cancels that. At resonance, VL plus VC equals 0, because they are 180 degrees apart. So V total is just the voltage over the resistor. So that vector plus that vector plus that vector is just VR. And there we go, there's a brief explanation of that. And of course these can be much larger than the voltage over the resistor. Right, let's go on to part B. I've done our old part, show that the voltages at resonance are both 79.6 and explain why voltages larger than the source voltage are created. So the key to it is that these are not in phase, 180 degrees apart. Let's write that down. VL, VC are 180 degrees apart. Incidentally, how do I remember which way round is it, which leads, what leads what in a capacitor and inductor? if I sit down and think about it, I can work it out. A cheap way, I just remember the word civil, and in a capacitor, I leads V, and an inductor, V leads I. Not a physical way, but it works, it does the job.